Last class, we learned about a bunch of different geometries. And we predicted some molecular geometries. Hopefully some of this is jogging our memories. Some of these slides. And we had some steps for predicting molecular geometries. And it looks like it's 4 simple steps, but there are really multiple steps baked in here because we have to be able to draw a Lewis structure for the molecule. Typically, this is not going to involve an expanded octet, but expanded octets can occur for anything that's in row 3, period 3, and lower on the periodic table. Those can have expanded octets. Once we've got the Lewis structure, all of our octets are satisfied, our formal charges are minimized. We need to determine the total number of electron groups around the central atom, the number of lone pairs, bonds, single electrons, etc. Single bonds and double bonds, triple bonds all count as one electron group. Each of those individually counts as one electron group. That will give us the electron geometry. The number of groups around it gives us our simple shape. Then if we have lone pairs in there as well, then our actual shape, our molecular geometry, we take our simple shape and we imagine what if one of those spots just poof, disappeared or was invisible, and that will help us get to our actual molecular geometry. Alternatively, we do have table 11.1 that showed up earlier in the slides. Here it is, the big table 11.1. You can also refer to this table instead to get our electron geometry and our molecular geometry. So it's a little bit involved. We can also do this for larger molecules. So if we have more than one interior atom, we can determine the geometry around each of those interior atoms. Typically, these are going to be easier, generally they'll be easier than some of the things that we can encounter when we've got just one interior or one center atom. That's because we're sort of limited in the number of bonds that we can have. So if we look at this compound, we've got our nitrogen over here on the left. Our nitrogen is bonded to 4 things. So if we were assessing our electron geometry, this would be tetrahedral because it's got 4 things attached to it. We poof one of those things away because there's a lone pair on there. So we get rid of one of those pairs, and now it's trigonal. It's got 3 things attached to it, but because of that lone electron pair, it's pushing the trigonal out of the plane, so it's not trigonal planar, it's trigonal pyramidal. We could also reference table 11.1. For our carbon, our first carbon on the left, this also has the electron geometry of tetrahedral, but it's 1, 2, 3, 4 bonds. 4 bonds, 0 lone pairs means that it's also tetrahedral molecular geometry. Then our second carbon has 3 groups, and so this is going to be trigonal. And because we've got just 3 groups, not 4 groups in a lone pair, it's trigonal planar, it's flat. So it would look something like how it's represented here on the left. And then our oxygen on the left, 2 bonds, 2 lone pairs. This would also have the electron geometry of tetrahedral. But then when we go to assess its actual shape, the 2 lone pairs means that it actually has the bent molecular geometry. If we were doing this molecule, the H3C on the left here means that 3 hydrogens bonded to this carbon. On the right, the OH means that the hydrogen is bonded to the oxygen. Something that's missing from this structure is that we typically omit lone pairs when we are drawing out structures, because generally chemists just know, all right, there's going to be 2 lone pairs on these oxygens. And if there's nitrogen, oh, it's going to have a lone pair of electrons on the nitrogen as well, from lots of experience and whatnot. So let's draw in those things that are missing. We've got lone pairs on the oxygen that we would have to come up with. You could do some electron counting to figure out that those need to be there. You could also look at, well, the oxygen's going to have 2 bonds. That's only going to be 4 electrons. It's going to need 4 more electrons. So it's going to have to be 2 lone pairs. How many things do we have bonded to this far left carbon? 4 things. It's got 4 electron groups. So its electron geometry is tetrahedral. That breaks down into 4 bonds, 0 lone pairs. So it's tetrahedral molecular geometry. What about our central carbon? How many groups do we have on our central carbon? A double bond also counts as 1. So this has 3 electron groups. Double bonds, triple bonds, both count as 1 group. So our electron geometry is going to be, it's our simple shape for 3. It's got a prefix for 3. Yeah, trigonal planar. The tri in trigonal lets us know that it's 3. And the breakdown, we've got 3 bonding groups. We've got 0 lone pairs. So it's also trigonal planar molecular geometry. And last but not least, our oxygen. How many electron groups do we have on our oxygen? The one on the right. Electron groups. What counts as an electron group? Yeah, so it's bonded to hydrogen. So it's got a bond to hydrogen, it's got a bond to carbon, and it's got 2 lone pairs. So it's 4. So 4 electron groups, 4 clumps of electrons around it. What electron geometry is that? What shape for 4? Tetrahedral. And the breakdown of that is that there are 2 bonding groups. And there's also 2 lone pairs. If we referred to table 11.1, it would tell us that this is bent. So the molecular geometries, these would be the actual shape around each of these interior atoms. And knowing what the shapes are, we can make a sketch of the molecule. So we can draw this out, but with the actual correct bond angles. And I think it would be best if we start from the central carbon. We'll draw that oxygen in the up position. It's trigonal planar, and so it's going to have bond angles of about 120 degrees. This is the Y pose, the YMCA Y pose, but upside down in this case. So imagine me doing the Y pose, but I'm doing a handstand instead. I will not be attempting to demonstrate that today. And it's bonded to an oxygen on the right. It's bonded to a carbon on the left. In reality, this bond between the carbon and the oxygen on the bottom is going to be slightly smaller than the 120 because of the double bond exerting its influence. It's a little bit bigger, so it's going to push the carbon and the oxygen bond to be a little bit smaller. And then for our oxygen and our carbons, we have to think about tetrahedral electron geometry. And we're looking for about 109.5 degree angles, so slightly smaller angles. Maybe that's a little bit smaller. And we've got our hydrogen there. And then our two lone pairs that are on there. For the carbon on the left, we're also looking for about 109.5 degrees to one of our hydrogens, and then we've got the other two hydrogens coming off. Usually they're basically staggered. We typically don't do, I'm saying we as chemists in general, because I think this is true, most chemists are not actually really paying that much attention to the bond angles that they're putting in here. Once you take organic chemistry, you just you draw everything at the same bond angles for the most part. But basically what we want to get out of this is that this is not actually flat in the middle. This hydrogen on the right is not coming off to the side straight out right. There's a bend here. There's a bend here. And one of these hydrogens is going back. That's the one that I've drawn on the left. One of these hydrogens is coming out towards us. That's the one that's shown slightly on the right. So there's some three-dimensionality to the structures that we're drawing. And our brains need to be able to turn this structure that we are given into this 3D structure. All right, what is the molecular geometry around the nitrogen in this molecule? The CH3 in the front is the same as this H3C that we saw in the structure. Typically, CH3 is written instead of H3C if it's like written out formula. But this means 3 hydrogens on the carbon's bonded to the nitrogen's bonded to the 2 hydrogens. So if we were to draw it out in a style similar to what we saw in the previous slide, it would probably look like this. So let's think about if we've got 2 bonds to hydrogens from our nitrogen, is this a complete Lewis structure? What would we be missing? Is nitrogen happy? How many bonds does nitrogen have in the diagram? It would have 3 bonds. Does it have anything else as written? No, just 3 bonds. How many electrons would that count up to for our nitrogen? 6 electrons. Is the nitrogen happy? Quote unquote happy. If this is a Lewis structure. What's our goal? An octet. We don't have an octet, right? We've got 6. This isn't boron, so it's not happy with 6. So that would inform us that we also need a lone pair. So we add a lone pair on, and now how many electron groups do we have connected to nitrogen? We've got 4 electron groups. The breakdown there is 3 bonds, or 3 bonding groups. one lone pair. Does that match trigonal planar, tetrahedral, trigonal pyramidal, or bent? For molecular geometry. Tetrahedral is the electron geometry. We've got 3 bonding groups and 1 lone pair. What is that shape? I'm hitting the pose. Trigonal, because there's 3 bonds. Is it flat or not? Pyramidal. So it's trigonal pyramidal. We got 3 bonds. It doesn't always mean trigonal, but here it does mean trigonal. That's our connection. And it's pyramidal because that lone pair is forcing those 3 groups out of the plane. It's not going to be flat. Expanding on shapes, we also get to deal with polarity with shapes. In a diatomic molecule, meaning we've just got 2 atoms that are bonded to each other, the entire molecule, all 2 parts of it, will be polar if the bond is polar. So for example, when hydrogen bonds to chlorine, chlorine has a higher electronegativity value. I think it's a 3.5 if I'm remembering correctly. And so we draw this arrow that's pointing towards the chlorine. It's pointing towards the more electronegative side. And we've got a positive part for the side that's less electronegative. So overall, the electrons are going to be held onto stronger by the chlorine. That means we're going to have higher electron density around the chlorine side. So we write in this little music note looking thing, which I believe is a lowercase delta, meaning that we've got a partial negative charge rather than a complete negative charge. And the other side gets a partial positive charge. So for diatomic molecules, it's pretty simple. If you have a polar bond, you have a polar molecule. If you have a polyatomic molecule, the polarity depends on the geometry, depends on the shape. If the dipole moments of the individual bonds cancel each other, the molecule will be nonpolar. If they don't, if we've got polar bonds and they're not canceled out, or if we've got slightly below polar bonds but they add up, then we can still end up with a polar molecule. And there's a couple of ways that we can think about this. There's a shortcut way that works a lot of the time, and then there's the much less fun, arguably, way that involves vectors, not the Despicable Me character. So CO2 contains 2 polar C double bonded to O bonds. However, the molecule is linear, so the bonds oppose each other. If we look at the structure down below, we've got our arrows pointing towards the oxygen. Since oxygen is a 3.5, carbon's a 2.5. So we've got arrows pointing in opposite directions. This would be like if my chest, my torso, is the carbon atom, and my hands are each being pulled on. These are the double bonds, because I've got big, strong muscles. No, if they're being pulled on by 2 big people on the outsides, but they're twins. They're the same size. They're enormous bodybuilders. They're both pulling on my arms. They're doing tug of war with me. I'm just going to be hanging limp in the middle. We're not going to be moving one way or another. So the pulls from either side cancel each other out. So the pull/arrows cancel out. So in a CO2 molecule, because the directions are opposite, they both point towards the more electronegative atoms. They're pointing in opposite directions, completely opposite directions, and their magnitudes are the same, then it cancels out. There's no overall effect. So the bonds are polar, but the molecule is not polar, which means it's nonpolar. Non basically just meaning not. Water contains two polar OH bonds. Because the molecule is bent, it's got two bonding groups and two lone pairs. It has bent molecular geometry. Can draw in our two lone pairs. One would be coming out of the board, one would be going into the board. So these HO bonds are both flat in the board. We can see the arrows are both pointing in and up. If we were to separate, when we do the vector part, this is the arguably less fun way. So with vectors, what we do is we separate them out into a vertical component and a horizontal component. And if it's not in 2 dimensions, then we get to add a third dimension that's like the in-out component. So we can see if we separate it out, the left arrow and the right arrow, right, these are going to cancel each other out, but the up direction arrows do not cancel each other out. They're both pointing in the same direction, and so they add up. So just pulling out the arrows. Those two arrows cancel. These two arrows add. So overall, we would just get one big arrow pointing up. We add the two arrows. You just stack the arrows on top of each other. They add linearly. And so it's polar overall, because those arrows don't completely cancel out. Again, I think the vectors is probably the least favorite way of people to do it, but it works for everything. Again, not super fun, necessarily. All right, if we want to figure out the molecular shape and the polarity, we need to draw the Lewis structure and determine its molecular geometry. Remember that drawing the Lewis structure was step 1 from what we talked about at the top of the class. So that's multiple steps. And then we also determine its molecular geometry. And that's more multiple steps. It's a little bit of counting. And then we get to add some more steps on top of that. The new steps that we're adding on is determine if there are polar bonds. Polar bonds, just as a reminder, have a difference in electronegativity of about 0.4 to 2.0. If it's below 0.4, it's nonpolar. If it's above 2.0, it's ionic. And we can indicate those polar bonds with vectors. They're pointing towards the more electronegative atom, and the length should be about equal to the difference in electronegativity. If we're doing the vector approach, we'll learn a shortcut. Then we need to determine, do the polar bonds, do our arrows add up or do they cancel out? And so that's when we separate them out into their separate directions. If the vectors sum to 0 or near 0, the molecule is nonpolar. If there's a net vector, aka if arrows don't cancel out, then the molecule is polar. 0.4 or below for the difference in electronegativity for a bond, it's nonpolar. They're like loose thresholds. It really is on a continuum, so it's at varying degrees. It's sort of like asking somebody what would make somebody like averagely strong versus weak or super freakishly strong. And you said, well, if you can do like body weight squat, deadlift, and like 75% of your bench press, then that's like maybe the lower end, somebody might say. If you can do double your body weight for your squat, your deadlift, then that would be like the upper end of average strong. And if you can do more than that, then you're freakishly strong. There's not like actually a real hard cutoff. It's sort of a continuum. The bigger it is, the stronger it is.
Okay.
It's nice to have numbers so that we can quantify it. We can put words to it. But it is on a continuum. These are just our rough thresholds. These are the numbers that you'd memorize, though. But there's that little asterisk, invisible asterisk. All right, a molecule contains 3 identical polar bonds. Polar bonds. It's a trigonal planar molecule. Is the molecule polar? Draw out trigonal planar and figure out, do the arrows add up? If they're all identical bonds, do they not add up? I'll give you a minute or so. All right, we're looking at 3 identical polar bonds in a trigonal planar molecule. Trigonal planar is going to mean that we've got our center atom, and we've got 3 groups on it, and they're evenly spread out. They're flat, which is nice and easy. So this is our Y-shaped, and we'll draw it in the Y shape. So we've got something down there, and we've got 2 things up to the right, 1 to the left, hitting the YMCA pose. If they're all identical, then the arrows should all be the same length, which I'm doing a terrible job of. So it would look something like that. And the arrow up to the left and up to the right, if I had drawn them well. They are going to have a left and right component. Those are going to be the same size rather. Those will cancel out. And then the upward components should add up to be the same size as the down arrow. So because all of our arrows are pointing in nice, evenly spaced directions and they're the same magnitude, they cancel out completely. So this molecule is not polar. This ties in with the shortcut that we'll be learning pretty soon. Let's look at, I'm just going to like breeze through this because I'm assuming that none of us are going to want to do the vector addition method. The way that the vectors work. Vectors in one dimension, they lie on the same line. You can assign a direction as positive, just arbitrarily, whatever direction you want. Probably you're assigning right to be positive and left to be negative. If you've got 2 arrows that are both pointing in the positive direction, that's to the right, and they're both +5, they add up. The total size of that is +10. Just adds up, whatever the length we've determined is. If you've got an arrow that's -5 and one that's +10, then that's an overall of +5. Simple addition. A -5 and a +5 are going to cancel out entirely. If we've got more than one dimension, that's when we get to do the thing that I've been doing, where you split them out into their different components. Here it's showing them as a parallelogram, so something with 4 sides and 2 pairs of parallel lines. So the top dotted line and this B vector, or this B arrow, those are both parallel. The right dotted line is parallel with A. And you can turn them, you can do all sorts of stuff with those. So that's splitting them out. If you've got more directions, you can do all sorts of fun stuff. You can also make these into their X and Y components and add them up. However, we can also boil it down to a couple of common cases. For our simpler shapes, when we're not doing expanded octets, this is typically when we're going to look at if something's polar or not. We've got a couple of cases. We've got linear with polar bonds. They're pointing in opposite directions. This is like the CO2 that we were looking at. The arrows are in completely opposite directions. They cancel out. We can also have a trigonal pyramidal shape. This is going to end up being polar. The side arrows, or sorry, this is bent. The left and right components of these 2 arrows cancel out. The up component adds up. And so that'll end up being polar. If we have trigonal planar, where we've got all 3 groups the same, this is the conceptual connection that we were doing before. This is going to be nonpolar because these arrows all completely cancel each other out. Tetrahedral will also completely cancel. If we have trigonal pyramidal, that's tetrahedral, but we've replaced the up thing with a lone pair. So drawing in the phantom thing there. Get rid of it. These, the 3 directions, is going to look, if we look from the top down, is going to look like trigonal planar, but they're all pointing slightly away. There's nothing to cancel out that slight away direction that they're pointing, and so that part is going to cancel or add up. So that's why we get the little red arrow. So the red arrow is the net polarity. So after you've canceled everything out, the red is the little bit of leftover. This is assuming that all of the bonds are equal. This leads us into our shortcut. This is Mrs. K's shortcut to molecular polarity. A molecule is nonpolar if both of these 2 conditions are true. So there's 2 conditions that we have to meet. Condition 1, no lone pairs on the central atom. So we're checking, do we have lone pairs on the central atom? If there are no lone pairs on the central atom, then we proceed to check 2. All of the atoms are the same or have the same electronegativity. All bonds are the same. If both of these conditions pass, then it's nonpolar. If either of these fails, could be polar. It won't always be polar. A lot of the time it will be polar, but it won't all the time be polar. It just means that it could be polar. So because this is a fast way of determining if something is polar, specifically if determining something is nonpolar, I prefer to call it the nonpolar shortcut? No, the nonpolar express. Punch your ticket today. This is what I usually recommend people learn because I think that it's It's just objectively easier, I think, than the vectors. Vectors is more robust. It's better if you can do it, but this is a nice shortcut. Please note that this requires polar bonds. So the way that this works, no lone pairs on the central atom means that it's going to be one of our simple shapes. All of our simple shapes, because of the way that valence shell electron pair repulsion theory, all of our simple shapes are linear, is if we've got 2 bonds, are trigonal planar if we've got 3 bonds, tetrahedral if we've got 4 bonds, are trigonal bipyramidal if we've got 5, and are octahedral if we've got 6. Those are all perfectly evenly spaced out. So the arrows, the vector arrows that we would draw are all nicely, perfectly evenly spaced out. If the arrows are all the same size, then they all cancel out, and it's nice. So that's why this nonpolar express works. All right, let's determine if CF4 is polar. I'm going to assume that we can draw the Lewis structure, and so I'll just give it to us. CF4 looks like this, with lots and lots of lone pairs. First thing we want to check, do we have a polar bond between carbon and fluorine? What is fluorine's electronegativity value? It's the one that we should know. What's a perfect high school GPA if you didn't take AP classes? 4.0. Fluorine's got a 4.0. Carbon, not quite as good of a student. 2.5. If you've got your yellow sheet, the electronegativity values are on there. So we've got an electronegativity difference of 1.5. Is that a polar bond? Yes, it's between 0.4 and 2. So we've got a polar bond, so we do need to check if it's actually polar. If it was not a polar bond, then we wouldn't even bother checking. Let's go through our nonpolar express. First point on the nonpolar express. No lone pairs on the central atom. Do we have no lone pairs on the central atom? Is the statement there are no lone pairs on the central atom true? Yes, it's true. This part can be a little bit confusing. No lone pairs, there's 9 there. No lone pairs on carbon. Check, that's true. Our second point in the nonpolar express. Because that was point 1. Point 2, all bonds are the same. Is that also true? Yes, it is. Both points check, so is it polar? No, it's nonpolar. It's the nonpolar express, not the polar express. The polar express is a film that we watch at Christmas time. So if both points check, if both points pass, it's nonpolar. So CF4 is nonpolar. We could also do it with the vector addition method, but I don't want to do that. This is annoying to draw in 3 dimensions. What's the point of polarity? The point of polarity is that polar and nonpolar molecules have different properties, the way that they interact. Oil is nonpolar. Nonpolar molecules, especially things like oil, interact more like friction. They're long, sort of like noodly shapes, and so they get tangled up with each other. Think if you make spaghetti or linguine or fettuccine or any other long pasta, and you finish cooking it, you dump all the water out, or you run it through the strainer, you throw it back in the pot, and you leave it for a little bit, and then you try to pull out, I'm going to just pull out a couple strands of spaghetti. Good luck, right? It's going to glob onto all the other pieces of spaghetti because they're all stuck together. They've got lots of surface area, and so they connect that way. Water is polar, and polar molecules behave much more like magnets. There's partial positive and partial negative sides that can link up, and that makes for strong attractive forces between them. And so if you mix water and oil, the oil is going to stick together with that like long spaghetti friction-like action. And the water, because it's polar, it's like little magnets, it's going to clump up and expel the oil. And so they're always going to separate out. Generally, polar and nonpolar things don't work, and that's where soap comes in. So soap has special features to it, special chemical structures on it that lets it interact with both. Water's polar, grease, oil, nonpolar. Soap molecules have a long nonpolar tail. They've got that spaghetti shape on them that lets them interact with that surface area, lets them get tangled up with the other nonpolar molecules. And it also has a magnet head, the polar head, that can interact with water. So soap is a bridge between water and grease or oil. And that lets them connect to each other. It's sort of like if you're trying to hook up a trailer to your truck, if you have a truck, and you don't have a hitch, good luck. The soap, in this case, is the hitch. You add it in there, and it lets the truck connect with the trailer. Without it, again, good luck. So it's got the part that connects to the water, it's got the part that connects with the grease or the other nonpolar things. This is why if you try to wash grease off your hands with just water, it doesn't work very well. But you add soap in the mix, and boom, magic. There's lots of different things that have soap-like properties. It's just the general having a polar head and a nonpolar end as well. Questions about polarity so far? All right, we are also going to get into bond theory, which we didn't really talk about very much in Chem 20. So a lot of this stuff is new versus the polarity was mostly review from Chem 20. So the Lewis model is an oversimplification. The Lewis theory, the Lewis structures that we were drawing, it's a simplification. We can add more advanced theories in. Modern quantitative approaches with numbers. Quantitative means there's numbers and measurements involved. Modern quantitative approaches can predict a lot of properties, but they're very, very complicated. We're not going to be doing any of those. So we're not going to invoke too much in the terms of numbers. We're going to look at some of the theories in qualitative manner. No numbers or few numbers. So this is like the difference between saying, I can run a 5-minute mile versus I'm really fast. Saying I'm really fast applies to kind of a broad spectrum, and it sort of depends like the context. Saying I can run a 5-minute mile, you're putting a hard number to how fast you are and in what context you're fast. So our electrons, if we remember a couple chapters back, our electrons reside in quantum mechanical orbitals. Orbitals like S, Px, Py, Pz, etc., different shapes within shape families. And these are localized. They're set in one area. They're around individual atoms. They can be S, P, D, and F orbitals. They could also be hybridized atomic orbitals that blend two or more of our atomic orbitals, and we will be talking about that at some point. When two atoms approach each other and they're saying, hey, maybe we should think about bonding, the electrons in the nucleus of one atom are going to interact with those of the other atom. Our valence bond theory, we're going to need to look at energy changes from those interactions. A bond forms if the energy of the system is lowered by the interaction. If it's not stabilizing, if they don't get along, a bond is not going to form. This is similar to the way that we as humans interact. If you approach somebody and you meet somebody, as you approach and as you interact, you're interacting with each other. The things that you're saying, your body language, the things you're interested in. And you might become friends, you might form a chemical bond if there's some shared agreement, if there's some shared understanding, if there's some similar common interests. So looking at two hydrogen atoms that are approaching each other to potentially bond. If we've got two hydrogen atoms and they approach each other to bond, initially they're going to start out far away from each other because they have to approach each other still. So on our x-axis, we're looking at distance. Further away is to the right, closer together is on the left, and the energy level is on the y-axis. So 0, our baseline, just there's no change in their energy. If we're going below that, then that means that it's stabilizing. If we're going above that, then it's repulsive. So above is bad, below is good. Initially, when they're at this distance from each other, they are a little bit stabilized. And so because of the way that things randomly move around, they move closer together, their energy drops more, they move closer together still, and they reach this happy, nice middle ground. Maybe they move a little closer, and they're like, hey, this is a little too close. Maybe back it off a little bit there, bud. And so eventually they're going to settle into this nice, level of friendship. They find the distance, the relationship that works for them. And they will settle into that. The interaction energy is usually negative or stabilizing when interacting atomic orbitals contain two electrons that can spin pair. So the orbital diagram this involves using an orbital diagram. We'll see examples of that. We need to have two electrons, typically from half-filled orbitals, that can go together. So if we've got two hydrogens, they approach each other, they say, hey, can we bond? We've got one up, we've got the other one up. It's easy to flip one from up to down. And now they're spin paired. So this is the typical case that we see for bonding. The electrons come from two half-filled orbitals. We can also have, let me draw that line better. We can also have two electrons come from a filled orbital and it overlaps with an empty orbital. So one atom gives both electrons. And this typically is going to happen with metals as the centers and some other thing as the other part. These are coordinate covalent bonds. I think that we might touch on these a little bit later. If not, you'll cover them in Chem 2. So the super fast summary of valence bond theory: valence electrons of atoms reside in quantum mechanical orbitals. S, P, D, F. Typically, we'll just be looking at S and P. A chemical bond results from the overlap of two half-filled orbitals. So two half-filled orbitals pair. the geometry of the overlapping orbitals determines the shape, and we'll be looking at this next. So the shape of the bonds equals the shape of the molecule. How all those shapes interact. And it should generally work with our Lewis theory. It should match with our Lewis theory. If we look at H2S, so we're looking at H2S. The actual bond angle is 92 degrees. Valence bond theory predicts 90 degrees. Valence shell electron pair repulsion theory predicts just less than 109.5. So what we're looking at, we've got hydrogen's orbital diagram, another hydrogen's orbital diagram, and we've got a sulfur's orbital diagram. Notice that we've got these two unpaired orbitals. These are half-filled, which means that they are ready to pair, or that they can pair. They're available to pair. And so if these hydrogens approach, one of the hydrogens can pair with the first unpaired electron, the other one can pair with the other unpaired electron. And these are p orbitals. P orbitals are at 90 degrees from each other. So we've got one that's going straight up and down, we've got one that's going perfectly left and right, and then our third one would be going straight in and out. And so those are at 90 degrees to each other, and so what we would expect, based on valence bond theory, is because these are 90 degrees from each other, one of the bonds is going to be sticking out directly to the right, one of the bonds is going to be sticking directly out towards us, would be one of the options. So we would expect it to be 90 degrees, hydrogens interacting with one of the p orbitals, this other hydrogen interacting with one of the other p orbitals. And that's pretty close to what we see in the actual 92-degree bond angle. Let's see if we remember what a chemical bond is. What is a chemical bond according to valence bond theory? Is it a lone electron pair? Is it the overlap between half-filled atomic orbitals on two atoms? Is it the overlap between filled atomic orbitals on two atoms? Or is it a shared electron pair between two atoms? It is B, overlap between half-filled atomic orbitals because they can spin pair. And that's how they fill out the bond. However, this doesn't always work nicely. So the overlap of half-filled standard atomic orbitals does not explain bonding in many molecules. For example, between carbon and hydrogen, carbon has this orbital diagram. Notice that we've got two unpaired electrons. And so what we would expect, if it's half-filled orbital is overlapping, we would expect you've got two unpaired electrons, we can pair that with two other things. So we would expect two hydrogens to come along. Let's draw in the other hydrogen. And just like we did with H2S, one pairs with the first one, the other one pairs with the second one, and we would form two bonds, and they would have 90-degree bond angles. But what we actually see with carbon and hydrogen bonding together is tetrahedral shape. So we need to expand our theory a little bit for this to work. And this is where hybridization comes in. So the orbitals in a molecule are not necessarily the same as the orbitals in an atom because of hybridization. Hybridization is essentially blending orbitals together. It's a mathematical procedure. We're not going to do any of the math. The atomic orbitals are combined to form hybrid orbitals. The number of atomic orbitals in equals the number of molecular orbitals or hybrid orbitals, I'll write for now, out. So if we put in 2 atomic orbitals, we blend them together, we'll get 2 hybrid orbitals out. If we put in 3 atomic orbitals, we'll get out 3 hybrid orbitals. And these end up having shapes that we are already familiar with because we talked about them in valence shell electron pair repulsion theory. They're going to look a little different, they're going to sound a little different, but the shapes are things that we've seen before. I'm going to go ahead and box this in, and we'll underline it too. So hybrid orbitals minimize energy because they maximize orbital overlap. If you remember, our s orbital is just a round sphere, and our p orbitals are sticking out at those 90-degree angles. It makes it hard to access that s orbital on the inside because of the way the p orbitals are sticking out. So what hybridization does is it says, let's mix them all together and come up with other options where that s isn't just so localized. We can get a little bit more access to it by blending it with other things. So the hybrid orbitals get better overlap because of the way that the probability works out. It does require energy, but it's going to happen. Atoms that form more bonds are more likely to hybridize. We are going to focus on hybridizing interior atoms. Terminal atoms, ending atoms are unhybridized, which is nice. Some general statements. This is actually important stuff. This is what I wrote down 2 slides ago. The number of standard orbitals added together always equals the number of hybrid orbitals. 2 in, 2 out. 3 in, 3 out. What if we put 4 in? We get 4 out. So the number that we put in is the number that we get out. The combinations of the standard orbitals that we add together determines the shape and the energy of the hybrid orbitals. There's only a couple of options for these. The type of hybridization that occurs is the one that yields the lowest energy for the molecule. We're going to use valence shell electron pair repulsion theory, electron geometries to predict hybridization. So the electron geometries, things like linear, right? That was if we had 2 groups. I don't know, I wrote groups. That shouldn't be an A, that should be an O. We had trigonal planar, that's the flat one, with 3 groups. Tetrahedral with 4 groups. 5 was trigonal bipyramidal, 6 was octahedral. So trigonal bipi, 5 groups, octahedral, 6 groups. So we're going to be using these 5 shapes to determine or to predict our hybridization. So these 5 shapes will be important. We're going to start off with our sp3 hybridization because this connects directly back to our CH4. So here's what happens. Here's our standard atomic orbitals for carbon. Our 2s is going to be lower in energy than our 2p. That's why we fill our 2s orbital before we fill any of our 2p orbitals, because it's lower in energy. What we can do with these 4 orbitals is blend them together. We hybridize them. So we put 4 in. How many do we get out? We get out 4. And the label for these is sp3 because we blended the s with 3 p orbitals. So the total, if we've got 1 s orbital and 3 p orbitals, we're going to have 4 orbitals. And now we've got 4 up arrows. So we've got 4 half-filled orbitals. That means that we can do 4 bonds, which is what carbon likes. Carbon likes having 4 bonds. And the energy of these sp3 orbitals is between the p and the s. It hybridized, the energy level sort of balances out. And the 4 hybrid orbitals are degenerate. Huh? What does degenerate mean? Does it mean they're good for nothing, low down, dirty dogs? To quote Barty? No, it means that they're the same energy level. Or equal energy level. So they're all equal in terms of their energy level. We call that degenerate, which I think is funny. It's really the only reason that I define it is because it's funny. And here's what they look like. So we blend our s with 3p orbitals. Here's our s orbital, px, py, pz. They're along the x, in, out, y, left, right, z, up, down axes. We combine these together, and we get these fun sp3 hybrid orbitals. They're all equal in terms of energy, and they all kind of look like bowling pins. And they're spread out with 109.5 degree bond angles. This is tetrahedral. That's that tetrahedral shape. We've got 1 pointing up, we've got 2 pointing down and out, we got 1 pointing back, or however you want to rotate it. There's a bunch of different ways you can draw it. But this is our tetrahedral geometry, and that's because tetrahedral is 4, sp3, the 1s plus the 3 p's equals 4. So sp3 is always going to be tetrahedral. In terms of its shape. Our orbital diagram shows that we've got our 4 half-filled orbitals. They've got parallel spins. They're degenerate. They're the same energy level, and so they're all going to be singly unpaired first, and then if we had more, then we could pair them up. And we've got 4 of them. So with our valence bond theory, 4 half-filled electrons, or 4 half-filled orbitals, can bond with 4 half-filled atomic orbitals. Hybrid orbitals can also accommodate a lone pair, like if we have nitrogen. So in ammonia, which is NH3, so we've got our nitrogen in the middle and then 3 hydrogens bonded to them. This is also going to be sp3 hybrid orbitals. Nitrogen has 5 electrons, and so when we do the hybrid orbitals, on nitrogen, we've got 3 half-filled orbitals, hybrid orbitals. We can only form 3 bonds. And then the last set is our lone pair. Just for some explanation on that slide. How many sp3 hybrid orbitals result from the hybridization of 1s and 3 p orbitals? N equals out. How many n? How many are we blending together? How many are we hybridizing together? 4. So we're putting in 1s, we're putting in 3 p's. The 1s plus the 3 p's gives us 4. 1 plus 3 is 4. And then the hybridization label is sp3. sp3 just means blended or hybridized from 1s, 3p orbitals. sp3 has 4 things in it. It's got 4 groups because, again, 1s plus 3p. So it's always going to be tetrahedral in terms of its shape for these sp3 hybridized orbitals. So the correct answer, 4. We can also have sp2 hybridization, and we get double bonds when we do sp2 hybridization, or we frequently get double bonds when we do sp2. So 3 sp2 hybrid orbitals form from 1s and 2p orbitals. 1 plus 2 equals 3. So there's 3 sp2 hybrid orbitals. And that means that we have 1 unhybridized p orbital left over. So in our diagram, our 1 unhybridized p orbital is shown here. We hybridize the other 3. So we've got our sp2 hybrid orbitals. We also have our leftover p orbital. Three groups. Our electron geometry would be trigonal planar. So our YMCA Y shape. So this is the shape of our hybrid orbitals. And then we also have 1 p orbital that's left over, and this would be like if somebody came running through the door and skewered me through the chest with a giant spear. Arguably the most graphic way that I could have described that. So I've got also this p orbital that's unhybridized coming out from me and going behind me. So looking at those sp2 hybrid orbitals, look at that. It's that trigonal planar shape between our hybridized orbitals. If we look at something like H2CO, which we've done the Lewis structure of before, we've got carbon, oxygen, hydrogen. Our carbon can hybridize. It hybridizes to form the 3 sp2 and the 1 p that's unhybridized, that's left alone. So we can get 3 bonds with our sp2, and our p can also bond. Our unhybridized p orbital can also bond. These 3 bonds are going to be spread out in that Y shape. It's going to be that trigonal planar shape. But our p unhybridized orbital is also going to be able to bond. And here's what that looks like. Here we're trying to show it in 3 dimensions. So we've got this green plane that's flat, like a table. And we've got one of the hybrid orbitals bonding with a hydrogen that's coming out in the front. So it'd be like this. One coming out in the front, one going back behind. And then we've also got the CO bond that's going straight. But we've got a third thing, or a fourth thing, and that's the p orbitals. The p orbital from carbon that's unhybridized interacting with a p orbital from oxygen. And this is sticking up. It's also sticking down. So this raises a fun new topic for us, which is different types of bonds. So we've got 2 different types of bonds that we can have, or 2 different ways that we can classify bonds, either as pi bonds. Pi bonds are from p orbitals overlapping side by side. And we also have sigma bonds, and sigmas are end to end. Sigma is single bond. These are end to end bonds. And these are very strong. This is the handshake of a bond. You reach out and you, like if you watch an action movie and somebody's falling off a cliff, and then Dwayne "The Rock" Johnson reaches out and their hands, like they're grasping each other's forearms, right? That's a really secure hold. That's our single bonds, that's our sigma bonds. That's what we're doing here. Our pi bond is a side-on bond. And so rather than a direct grabbing the forearms like in an action movie, this is more like if you're reaching your hands out to the sides and you're like holding on to each other like that. Like you go to do a high five, but then you grab each other's hands. That's not going to be very secure if you're trying to keep each other from falling apart, pulling apart from each other, because you're way out to the side. You don't have very good leverage. So our pi bonds are much weaker, and they stick out at these weird 90-degree angles from our sigma bonds. And we will talk more about sigma and pi bonds on Wednesday.